All right, so next up we have Tsung-Cheng Liu from UMD talking about mixed state, long range order, and criticality from measurement and feedback. Take it away.
Yeah, okay. Hello, everyone. So I'm Peter Liu from University of Maryland. So I just recently joined there to be an RQS postdoc. So today I'll be talking about some interesting application about using measurements, the mid-circuit measurement and feedback to try to efficiently engineer some interesting many-body states of matter. So this is mostly based on the work with Zehao, Sagar, and Tim. All right, so as we know, if you have some quantum devices, they can be very useful for quantum simulation and quantum computing, right? And in particular, one essential task is about the state preparation. That is, quite often, you want to prepare the so-called long-range entangled states, including the GAZ state, torical states, different topological order states, or even a quantum critical states, because not only they are interesting from the physics standpoint, they can be very useful for different quantum information processing tasks. However, being long-range entangled, at the same time, that means it's kind of hard to prepare those states in the quantum devices. In particular, if you want to prepare this kind of long-range entangled states using unitary circuits, they cannot be prepared in constant depth, right? Just intuition, just because there's a light cone in the unitary circuit. So in order to generate some long-distance correlation or quantum entanglement, the preparation time need to grow with the number of qubits. So that means it is not like a scalable approach with unitary circuits. In particular, quantum devices we have right now, the qubits may decohere very quickly. So if you want to prepare some useful state, you better prepare the state as fast as possible, right? Hopefully in constant depth, right? So question is, can you avoid this fundamental limitation of the unitary circuit to try to efficiently engineer some interesting many-body states of matter? Indeed, so recently we know that with measurement as an ingredient, you can actually prepare many interesting many-body states with long-range entanglements in constant time. So here's the basic idea. Imagine you start from some product state of qubits. You may want to apply a few layers of a unitary gate, right? And then you select some qubits, you do the mid-circuit measurement. So here, for the future unitary, when you want to apply, the local choice of the unitary depends non-locally on the entire measurement outcome you have, right? Which requires the non-local communication of the classical data. So it is this kind of hybrid approach, like locally quantum, but non-local classically, right? It is this kind of hybrid approach with measurement and feedback that can try to efficiently prepare many interesting long-range entangled states, including different topological order, different long-range order states. So in recent years, there's been lots of promising protocols in these directions. Yeah, indeed, the protocol are kind of promising. So right now, these days, some of the interesting many-body states of matter with different topological order has been realized in experiments. So I want to point out that with measurements, that can be really inspiring. So there are many open questions with measurements. In particular, you can ask, what are the classes of long-range entangled states that can be efficiently prepared in this way, right? That is the fundamental question we want to ask. And the related question is, how stable are those protocols, right? Imagine you have some imperfect unitary operation or some imperfect measurements, then how stable are those protocols for preparing the long-range entangled state? So here's a simple example. Imagine you have the 1D cluster state, so just some qubits, some many-body state like in the 1D lattice. So like 2 decades ago, people already know that if given this cluster state as a resource, if you select some qubits, you do some single qubit measurements. Of course, as we learned from the basic quantum mechanics, you cannot control the measurement outcome in the sense that the measurement outcome must be random, right? That is the basic thing we learned from quantum mechanics. But right now, the crucial thing is, okay, so when you do measurements, you get a bunch of ensemble, right? Because you can have an ensemble of pure state trajectories corresponding to different measurement outcome. But right now, the crucial key point is, depending on the measurement outcome, you can always find a simple unitary feedback so that every possible measurement outcome state can be converged again to the same target state. In this case, that would be like a GAZ long-range order state. So overall, this is a deterministic process. Even though after measurement there's some randomness, but you can always find the appropriate simple feedback to try to deterministically prepare some targets that you want. So this is the ideal protocol you should have in mind. On the other hand, you could imagine I gave you some resource states, but unfortunately, there are some perturbation. So you no longer have a pure cluster state. You have some other pure states slightly away from the cluster state. So then, a priori, you may not know, right? But so then you may want to do the same measurement and the same feedback protocol on this imperfect cluster state. So generically, after this kind of imperfection, the perturbation on the initial state, different trajectories, they will no longer converge to the same target state. So instead, you should say that the final state you prepare is actually a mixed state, which is an ensemble of all these possible trajectories corresponding to different measurement outcome. So here, the crucial question is, because given that you prepare the mixed state, is the mixed state long-range entangle or not? Does it have the same long-range order, just like a GSE type of long-range order? Okay. So with this kind of questions that kind of motivate this work, so basically the essential insight is, independent of the initial state you have, whenever you do the measurement and the feedback, you are just implementing some non-local quantum channel. And what is that good for? That means if the initial state, they are having some universal properties, meaning that all of the initial state, if they belong to the same quantum phase, then we can just prove that when you do measurement and the feedback, all of those pure states can always be converted to the corresponding long-range entangled states, independent of the details of the initial state, right? And as I mentioned before, when you add some perturbation for the initial state, different trajectories, they will no longer converge to the same target pure state, generically speaking. So actually, you realize a mixed state ensemble for the final state, but nevertheless, they can still display some interesting quantum long-range order or some quantum criticality, and they can emerge in constant depth. So to remark, so from the QI perspective, that means this insight can demonstrate some robustness of the protocols, because when you do the measurement feedback, you don't need to worry so much about the details of the initial resource state for generating the long-range order or long-range entanglement. And from the quantum matter perspective, that means it's kind of interesting to engineer some interesting many-body mixed states of matter where you have a bunch of like a classical fluctuation, but you can still have some kind of long-range entanglement at the same time. So it is like a kind of non-equilibrium, non-trivial mixed states of matter, which is in contrast if you consider some generic mixed states, which is the finite temperature states. They are generically kind of trivial at any non-zero temperature, just because the thermal fluctuation is too strong. So, yeah, so this is the main result we have. So right now, let's just consider more details. So, okay, so let's just try to recall what is the cluster state. Imagine you have a 1D lattice of qubits. You can consider they kind of interact, and Hamiltonian is given by this, the following three-body interacting Hamiltonians. Okay, so basically, you have a 1D lattice. You can call the odd side to be sublattice A, the even side to be sublattice B. You have the coupling between A and B, given by this neighboring Z, X, Z type interactions. That is the Hamiltonian you have, and you can check there is the Hamiltonian satisfy two different symmetries. That is, it is invariant under the global spin-free symmetry on sublattice A, and also the global spin-free symmetry on the sublattice B. And the ground state of this Hamiltonian is the so-called cluster state, which can be prepared from a product state using a constant depth circuit. All right, so right now let's consider the possible deformation and the perturbation for the initial cluster state. So basically, you could imagine you want to perturb the initial state with a finite depth circuit, but right now let's just try to be restricted in the sense that you consider the symmetric circuit, in the sense that every gate commutes with the symmetry generator. So every gate, when you apply to deform the state, that is symmetric under the Z2 cross Z2 symmetry. Okay, so when you consider some particular symmetric deformation, you go to a different state per sign prime. But you can consider all the possible, symmetric deformation in constant depth, right? So that you can reach out, all the possible pure states. Then all the possible pure states that can deform in this way is called the SPT phase. In particular, if you consider a symmetric product state, then that is like a trivial SPT because it cannot be connected to the cluster states when you enforce the symmetry in the circuit. Okay, so that is like a basic definition for non-trivial SPT phase, where cluster states is only an example of the SPT phase. Yeah, so right now the claim is, no matter what state you give me, as long as the states belong to the so-called SPT phase, we can very easy to show that with the same measurements and the feedback, you can always engineer a corresponding long-range order with the GAC type of long-range order. Yeah, so this is one of the main results we have. So what is the idea? So the idea is the following. If you start from any pure state in the SPT phase, so it is non-trivial in the sense that it must have a non-zero swing order parameters. Okay, it's pretty simple to write down. Imagine you have some interval. You consider plot of x in the interval of the sublattice A, that is a plot of x, 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 x. And then on the boundary of the string, you decorate two poly z operator on the boundaries, right? And you consider expression value of this guy. It turns out for any pure state that belong to the SPT phase, you're gonna take a non-zero order one number, that is c equal to c. So the precise number of c depends on what is the exact state you are using, right? So it may be different for different pure state in the same phase. But the non-trivial thing is, what is universal is, as long as you are in the SPT, it's gonna have a non-zero order one number for the string order parameters. So that is a universal property of the SPT phase. And right now, let's see how do you generate a long-range order. So again, for the first layer, you select every qubit on the sublattice A, and you do the poly X measurements, right? That's simple. And then in the second layer, you do some on-site poly unitary on sublattice B, where individual choice depends on entire measurement outcome of the previous measurements. So the claim is you can generate a long-range order on the sublattice B. In particular, if you consider the 2-point function for the final state you have, you're gonna see some non-zero order one number. In particular, this non-zero order one number is exactly the original string order parameters. So it's just the same constants. So you are just exactly converting the non-trivial string order to be the 2-point function that can give you the long-range order. But on the other hand, if you only have a product state, right, every spin is pointing up, you also have the 2-point function to be non-zero, right? But what is non-trivial is, for the final state, you have another condition, that is the product of x is equal to 1. And it is the combination between these two conditions can guarantee the long-range entanglements. In particular, we can prove that the mixed state you have, the final state you have, cannot be written as an ensemble of a short-range entangled state. So therefore, it must be long-range entangled, just based on these two conditions. Yeah, all right. What is the idea behind this? So basically, we understand that when you do measurement and the feedback, that amount to you are implementing some unitary on the initial state, and then followed by tracing out the measured degrees of freedoms. In particular, the unitary you consider is determined by the feedback, unitary feedback and the measurement you have. In particular, it is that you sum over all the possible measurement outcome. So where different outcome correspond to different product state in A, and depends on the product state in A, you apply some simple unitary on B. So it is a control type of unitary in the sense that A is the control and B is the target, right? And it turns out this control unitary is pretty powerful. It is sufficient to implement some non-local transformation in the sense that if you just transform the original string order operator, you can kill every x in the middle, and then you only generate two poly z on the boundaries. What does that mean? That means if the initial state has a non-zero expression value in the string order operators, then the final state will have the same non-zero order one constant for the final state. So this is like a universal conversion from the string order to a long-range order. That is how we do this. So with measurement and feedback, that amount to doing a non-local unitary, and you trace out A. Yeah, so that is the basic idea here. All right, so let's move on. So you know, when people discuss the mid-circuit measurement and feedback, typically people only consider the Pauli measurement, right? You measure some simple Pauli operators, but certainly you can imagine if you measure something more non-trivial, maybe you can get something more interesting. Indeed, that is the case. Imagine you have some fermion system. You could imagine there's a protocol where you measure fermion occupation number everywhere, and you have some simple feedback. And in particular, this kind of measurement is already available in the quantum gas microscopes in experiments. So kind of interesting to explore the application of this fermion measurement. Yeah, so as a simple example, if you consider the 1D free fermion, the time-spanning model where fermion can hop around and the fermion can be spin up or spin down. So it is, we know everything about this model. We can write down the ground state. It's simple to write down. However, and in particular, you know, if you consider the spin-spin correlation function for this critical fermion system, it is like a 1/r squared decay. It is critical. These people know already. And on the other hand, there's also a hidden string order parameters for the critical fermions. That is, in addition to consider the spins here and the spin there, you consider the product of the fermion parity in between. So it is like a string operator where the ni is like a fermion number operator. So -1 to the ni give you 1 or -1, depending on whether the fermion is odd or even. So it's a fermion parity. So there's a string order parameters for the fermions, and people know that it decays like 1/r. And so here, I'm gonna skip all the details, but basically, if you start from this critical fermion state, if you first measure the fermion occupation number everywhere, you apply some simple feedback, you can exactly convert the string order to a corresponding two-point function, where the two-point function have this 1/r decay. That is pretty striking because initially the two-point function is like 1/r squared, but right now with the constant ZAP measurement and the feedback, you can convert 1/r squared to 1/r. So it turns out the finite depth circuit can be very powerful to manipulate the critical property and to enhance the critical property of your fermionic systems. So that is an interesting application in 1D. Right now, let's consider 2D. In 2D, for fermionic systems, you can consider the so-called chain insulator state. Basically, it is like an insulator in a bulk, but then it can conduct on a boundary. That is the defining property of the chain insulator state. And because it is trivial in a bulk, so if you consider the two-point function in a bulk, it decays exponentially with the separation between 2 points. On the other hand, what we can show is, given this chain insulators as an input state, if you first measure the fermion number everywhere, you apply some simple unitary feedback, you can actually engineer an output state so that the two-point function decays like algebraically. So that is a striking example where the criticality can emerge from a ZAP2 circuit, right? Because initially it's like an exponential decay correlation function, but right now it's like 1/r to some power decay, the algebraic decay. Yeah. So that is a striking example where what you can achieve with fermion measurement. Yeah. And I want to skip the details, but basically, as I mentioned before, when you do measurement and feedback, that can be regarded as a non-local unitary. And right now, that is the unitary that can transform between boson and the fermions. So that is a secret ingredient behind this kind of protocols. Yeah. So with this, let me just quickly summarize. So basically, we understand that any measurement and the feedback can be understood as a non-local channel that can generate some interesting long-range entangled states where different trajectories, they don't need to converge, but nevertheless, they can have some long-range entanglement in the mixed states. We discussed SPT to a long-range order, and we discussed some application with the fermion measurement. So moving forward, certainly, I think it's still a very promising direction to think about the utility and the limitation of the measurement feedback. And another thing is, which seems like we prepare some interesting many-body mixed states So I guess it's a fundamental question to think about how to classify those phases of matter and how to understand the entanglement structure. Yeah, so with this, let me just stop here and take questions.
Questions? Anyone?
Yes, thanks for the next talk. I guess maybe I missed it. Like, you talk about this mixed state order. Like, if you actually want to implement the dynamics and like the hardware has other form of like whatever imperfections and dissipation, like how robust are those type of dynamics against that, and how does that compare with the unitary circuit? I'm not sure if that question makes sense.
So if you want to consider some dissipation or?
Yeah, like, so you're proposing to use measurement feedback to prepare those states that can even be long range, kind of going beyond what will be available. But if you actually want to implement them on, let's say, noisy hardware, like how robust are they?
Oh yeah, that's a good question. So basically, right now we only consider some particular deformation for the initial state, but certainly you can add some decoherence for the initial state and to consider how robust of the long-range order for the final state, right? So in that case, yeah, the answer is we made some partial progress. So basically, as in the first part I discussed, if you start from a pure SPT, you can generate a long-range order. But you can imagine you add some decoherence for the SPT, and given that mixed state, then whether you can still generate the long-range order or not, right? So that is one of the questions. So I think the answer is yes, if the noise respects the symmetry. Yeah, so only for some particular type of noise, this protocol is robust. Yeah.
Are there cases where like you expect the symmetry to be sort of naturally respected in circuit hardware, or that's like a more abstract like?
Oh yeah, that's a good question. I'm not sure. Yeah.